Hello everyone to another edition of Symmetry in Newcastle. I hope that everybody made it despite the slight change in time. Well, it seems to have plenty of participants. So the first talk of today is given by William Hautekiet, and he will be talking about automorphism groups of transcendental field extensions.
Thank you very much. Thank you for giving me the opportunity to give a talk here. I have studied at the University of Ghent, and there I made my master thesis about automorphism groups of transcendental field extensions. And now I'm working at the ULB in Brussels as a PhD student and a teaching assistant. First, I will briefly recall some facts about algebraic Galois theory. So if we look at a finite Galois extension, then the automorphism group is always a finite group. And the subgroups of G are in one-to-one correspondence with the intermediate fields. So this is the famous Galois correspondence. And so given a subgroup G, H of G, the fixed field of H is the corresponding intermediate field. And conversely, when we take an intermediate field F, we can look at the Galois group of the extension L over F, and this is always a subgroup of the Galois group. When we look at possibly infinite algebraic extensions, we get that the Galois group is a profinite group. And this comes from the fact that every element of our field is contained in some finite Galois extension. And so we can write our big field as a direct limit, which corresponds to G being a projective limit or an inverse limit of those finite groups. So here, L over K is a finite extension, hence the automorphism group is a finite group. And in fact, these profinite groups are exactly the totally disconnected compact groups. And the topology that we define on this group is, in the case of Galois groups, is given by for a finite subextension L over small k. We declare the automorphism group of K over L to be an open subgroup. And now the Galois correspondence is a bit slightly different because only the closed subgroups of G will be into correspondence with the intermediate fields. The open subgroups then correspond to finitely generated intermediate fields, and this comes exactly from the fact that we declared this automorphism group of K over L for L finite subextension to be an open subgroup. That follows from the definition of the topology. Now, we might wonder what happens if we look at no longer algebraic field extensions, but transcendental ones. We will assume the transcendence degree of our field extension to be finite. And in that case, we see that the Galois group still has the structure of a totally disconnected locally compact group. The topology is in fact defined in the same way as the profinite case. So we declare the stabilizer of finite subsets of K to be open subgroups of the Galois group. And now to see why the Galois group of K over K is totally disconnected and locally compact, we will call these TDLC for short. We can take some element of our group different from 1. So that means that there is some element of our field that's not fixed, which implies that this group element sigma is not an element of the stabilizer of X, which is an open subgroup. But open subgroups are always closed, and 1 is always an element of the subgroup. So this means that 1 and sigma are not in the same connected component. But sigma was arbitrary, so in fact, the singleton 1 is a connected component. Which means that the group G is totally disconnected. On the other hand, the group G is no longer compact, but only locally compact. And that's easy to see because if we look at the automorphism group of K over this purely transcendental field K extended with T1 to Tn. Now this is an algebraic extension, so this will be a compact group. But it's also open because it's exactly the stabilizer of these transcendental elements T1 to Tn. So this will be a compact open subgroup of our Galois group G. Now, it is known that, in fact, every profinite group can be seen as the Galois group of some algebraic field extension. But for TDLC groups, there is not really known anything about whether a given TDLC group can be the automorphism group of a transcendental field extension. And that's in fact what the aim of my master thesis was, to look at some examples and to see whether we can look for some shared properties of Galois groups, or if we can say that every TDLC group is in fact a Galois group. I did not find a definite answer to this question, but so I did look at some properties of TDLC groups and try to interpret them as a Galois group. So in this talk, first we will recall some definitions on TDLC groups. Most of them were introduced by George Willis, who's present here. So I read a lot of his articles. Then we will say something about the Galois connection for transcendental field extensions. There will exist some kind of Galois connection, but the correspondence is quite a bit weaker. And then we will look at 3 concepts in TDLC theory and try to apply them to examples of transcendental field extensions. Okay, but first of all, I will give an example. I would call it the example because I will refer to it later for various choices of our base field small k. I got this from an article from the 70s from a guy, Alain Robert. But he just stated it and did some reasoning about the automorphism group, but didn't really look at any TDLC properties because the theory wasn't there yet. So we will take some base fields and add a transcendental element to it. And then for every n, we add the p to the nth root of this transcendental element to our field. So in fact, we get some chain of roots of this transcendental elements. I like to picture them just on a line. Like this. And now, first we will suppose that our base field K does not contain many p to the nth roots. So not many roots of unity, etc. And in that case, what can we do? First of all, we can send t to minus t, because minus t has the same properties as t, since we're assuming that we're working with an odd number p. So this is an involution, so we'll give already a cyclic group of order 2. Secondly, we can send t to 1 over t, again an involution. And then the third generator of the Galois group is in fact some translation on this chain of powers of p. So I will denote it by alpha. So alpha maps T to T to the power P. And so this gives a group which is isomorphic to the group of integers. So in total, we get this direct product. And so we see this is a discrete abelian group. Voilà. On the other hand, when k is a bit larger, if k contains p to the nth roots of unity for every natural number n, then we get a more complicated structure and more interesting structure for our Galois group G. In fact, when we look at the stabilizer of T, so which is by definition an open subgroup, then so T has to be fixed. But on the other hand, the pth root of T can to be sent to a multiple of it, and here zeta1 is a pth root of unity. So in fact, we can interpret zeta1 to be an element of the cyclic group of order P. And so zeta2 is then an element of the cyclic group of order P squared. But we need to end up with the field automorphism, we need a compatibility condition on these zetas. So in fact, zeta2 to the power P has to be equal to zeta1. Otherwise, this is not working. So we end up with exactly a compatibility condition on the projective limit on the cyclic groups. And so the stabilizer of T is isomorphic with the p-adic integers Zp. But that's not all, because we still have our translation alpha, which sends T to the power P. And when we let alpha act by conjugation on the stabilizer, we get exactly the stabilizer alpha T, or the stabilizer of T to the P. And if we take the union of all these stabilizer for higher powers of T, we get in fact exactly the field of p-adic numbers. And this alpha has an action on the subgroup. So in the end, we get this semi-direct product. Okay, let's now look at some basic definitions about TDLC groups. So examples, we already saw that the automorphism group of transcendental field extension is one, but also discrete groups are always TDLC groups. And compact, so profinite groups are also examples. But those two classes are in fact quite trivial, as we will see. Besides that, there are two large classes of TDLC groups. So we can look at automorphism groups of locally finite trees. And here the topology is defined in exactly the same way as for Galois groups. You take the stabilizers of finite sets of vertices to be open. And then on the other hand, you have the p-adic Lie groups. So for instance, over the field of p-adic numbers. Voilà. One of the first theorems about TDLC groups was the following, and this gives us a clue how to use this totally disconnectedness in real life. So the units of a totally disconnected group always has a local base consisting of compact open subgroups. So we will primarily work with these compact open subgroups, and we will denote the set of compact open subgroups as BG. And in fact, this is a discrete metric space where the metric is given by the log of this index. And this index is always finite because if V and W are compact open subgroups, the intersection is open. But V is a compact group, so the index has to be finite. And the automorphism group acts then isometrically on this set. So here, I mean automorphisms of the group G, so they are group homomorphisms with automorphisms which are also homeomorphisms. Now, the two main concepts that George Willis introduced are tidy subgroups and the scale function. So given a compact open subgroup V and an automorphism of the group G, we look at the following subgroups. So V plus is the intersection of the orbit of V under powers of alpha. So this is always a compact group. And V plus plus is then this union, and this will also be a subgroup of G, because the union is increasing. And V minus and V minus minus are defined in a similar way, but in fact looking at alpha minus 1 and the inverse of alpha instead of alpha. Now, a compact open subgroup is called tidy if firstly V can be written as the product of V plus and V minus in two ways, and secondly V plus plus is a closed group. Now, in fact, George Willis showed that V is tidy for alpha exactly when this the plus distance between alpha V and V is minimal over all compact open subgroups. And the proof used some procedure which makes an arbitrary compact open subgroup into a tidy subgroup. And the scale function, so the scale of an automorphism alpha, is then exactly this minimal value of this index. So the previous theorem, in fact, says that this minimum is attained when V is tidy. And also it doesn't depend on the chosen tidy subgroup. Okay, let's look again at the example. So if we look at a base field K with enough roots of unity, then recall that the Galois group was this semi-direct product, and the stabilizer was a compact open subgroup. The stabilizer of T was a compact open subgroup. So our large field K was exactly the base fields where these roots were added. So H is the stabilizer of T, and this means that alpha of H is exactly the stabilizer of T to the power P. But if T is fixed, then so is T to the power P. So this means that H is contained in alpha H, and as a consequence, H plus will be equal to H. On the other hand, H minus will be the trivial group because if we look at alpha to the power minus n of H, this will be the stabilizer of this root, but when we take the intersection, we fix in fact any generator of our field K. And H plus plus is then exactly the union of the stabilizer, and we already said that this was isomorphic to the p-adic numbers. But now we see that H can be written as H plus times H minus, and also the other way around, because that's clear. And secondly, H plus plus, which is this semi-direct factor, is closed. Is a closed subgroup. So this means that H is tidy for alpha. And hence the scale of alpha is exactly this index of the intersection of alpha H and H into alpha H, but this is the same as the intersection, the index of H and alpha H, but this is equal to P. So the scale of this automorphism is equal to P. So this already shows that the scale of an automorphism of a Galois group can be quite arbitrary. Okay. Now, when we work with transcendental field extensions, there are some tricky things compared to the algebraic case. And one of them is separability. It does not behave that well in the transcendental setting because when you take a separable field extension and an intermediate field, it does not follow that K over L is separable. On the other hand, in the notion of a perfect field is preserved. So in characteristic 0, that means that in fact everything is separate. But this shows that it's not really easy to define what a nice field extension is, as we say for Galois algebraic Galois extensions. It's not immediately clear what definition we should use to have a nice Galois correspondence in the transcendental case. But I will call these nice field extensions admissible. And two conditions have to be satisfied. First, the fixed group of G has to be our base field. That's the same as in the algebraic case. And in the algebraic case, this is already sufficient to have a Galois extension. But here we will be supposing something more, namely the existence of an intermediate field L, such that L is finitely generated over K, and K over L is Galois. And here I mean with Galois, algebraic and Galois. Okay. And now we are ready to look at the Galois correspondence. When we just have the first condition, if the fixed field of G is equal to K, then we have a one-to-one correspondence between the compact subgroups of G and the intermediate fields of L, such that K over L is Galois. But to say something more, we need K to be admissible. And in that case, there is also a one-to-one correspondence between those compact open subgroups of G and the finitely generated intermediate fields such that K over L is Galois. So here the finitely generated is crucial. And the second condition in the definition of an admissible field extension was exactly that this second set is non-empty. So when it's non-empty, then we have a one-to-one correspondence. And so this shows that every compact open subgroup arises as the stabilizer of some finite sets. So every compact open subgroup is in fact a stabilizer.
William, can I just ask a quick question?
Yeah.
Is this the same notion of admissibility as in Robert's article?
In yeah, this is the
Alain
same.
Robert?
Yeah,
Okay.
It's the same. It's the same thing. I took it from there. In fact, I should have noted it.
Okay, thanks.
So for these admissible field extensions, we have a nice equivalence. The Galois group will be discrete if and only if the field extension is finitely generated. On the other hand, for non-admissible field extensions, we don't have this equivalence. In fact, we already saw an example. In the first case, when K did not have many roots of unity, then we considered a non-finitely generated field extension, but our Galois group was discrete. So this shows also that in some cases, especially for finitely generated field extensions, the TDLC topology will not be of that much use. And for instance, when you want to look at purely transcendental field extensions, finite transcendence degree, then it's better to consider other concepts such as the Zariski topology on the group to be able to deduce interesting stuff. Okay, let's return to our question. So we want to know if there are some conditions that we can say that a Galois group must satisfy, a TDLC group must satisfy to be a Galois group. And the first thing we're going to look at are contraction groups. The contraction group of an automorphism of G is a set of group elements such as alpha to the power n of G converges to 1. And Glöckner proved the theorem that if G is a p-adic Lie group, then in fact every contraction group is closed. So I wondered if we can say something about contraction groups of Galois groups. But in fact, the answer turns out to be no. Let's look at an example. When we look at the field of complex numbers and we add the transcendental elements, and then these delta n's are the pth roots of is a pth root of t plus n. Now, an automorphism of this field. There are two types, in fact. So one is again a translation that sends delta to delta plus 1, and hence t is sent to t plus 1. But we can also multiply every of these delta n's by some root of unity. And so in that case, we get like a tuple, an infinite tuple of root zeta, pth roots of zeta for every index. And so here delta n is sent to a multiple of itself.
So what exactly does n range over here?
Here the integers. Yeah, sorry.
Mm-hmm.
And when we look at the contraction group of alpha, yeah, when we want to alpha if an element of this type is an element of the contraction group, the automorphism alpha moves everything to the right, in fact. So to end up with 1, we need these zeta p n, these roots of unity, the multipliers, to be equal to 1 for sufficiently low index n for some. Voilà. So this means that the contraction group is exactly this direct sum, but it turns out that this is not a closed group, and it's in fact dense in this component. So I think it's difficult to say something about contraction groups in Galois groups. They can be closed, they can be non-closed. Next thing I looked at are flat subgroups. And a subgroup of automorphisms of G is flat when there exists some compact open subgroups that's tidy for every alpha. So there is a common tidy subgroup for every element of our group of automorphisms. And there is an interesting subgroup of this, of a flat subgroup, which we call the uniscalar subgroup. And this consists of all the elements that have the scale. The scale of alpha is 1, but also the scale of the inverse has to be 1. And some theorems also due to George Willis and collaborators, I think. In fact, this uniscalar subgroup is normal, and the quotient is 3 abelian. So this means that if H is finitely generated, we can speak of the rank of this flat subgroup as being the rank of this 3 abelian group that is the quotient. We also have some sort of conversion. When we look at some finitely generated and abelian subgroup of automorphisms, then it is always flat. Now, when we apply this to our example, it's more interesting to look at the example in transcendence degree 2. So we add 2 transcendents and all their roots. And now the stabilizer of T and S is just 2 copies of these p-adic integers. And this will be again a compact open subgroup. But those are not the only automorphisms. We can also mix the S and the T. And so in the end, we get some general linear group over this ring. Because so the A, B, C, D, the entries here can have a denominator who is a power of P. But for the rest, they have to be integers to still be elements of our field extension. And then we take the semi-direct product with 2 copies of what we had before. And so here, this C2 is still sending T to minus T, and here S to minus S, and then sending T to 1 over T is in fact contained in this general linear group, and the same for S to 1 over S. Now, we still have those translation of our chain of powers of T that sends T to the power P, but now we can do the same with S. So I'm looking at the 2 automorphisms alpha, which takes the power of T, and beta, which takes the power of S. Now, these 2 elements commute, so they generate an abelian subgroup. And it turns out that H, which is the stabilizer of T and S, is a tidy subgroup for every element of this group generated by alpha and beta. We will say that the flat rank of G is 2, and with the flat rank, we mean the maximum rank of a flat subgroup H of inner automorphisms. So here we're looking at alpha and beta as automorphisms on our group, on our TDLC group by conjugation. So we see here that the flat rank of G is equal to 2, and the transcendence degree is also equal to 2. So one might hope to see some connection between the transcendence degree and the flat rank. But in fact, there is a little hope when we look at the next example. I will not give the details, but in my thesis, I studied an example which I also got from the article of Robert, where K over K is a field of some elliptic functions of transcendence degree 1. And the automorphism group was in fact flat as a whole. So there was one tidy subgroup of this group, such that every automorphism, inner automorphism, had a steady subgroup, this subgroup U. But when I looked at the quotient G by G1, it turned out that this was isomorphic to the multiplicative group of positive rationals. So this is a free abelian group of infinite rank. So yeah, there appears not really be any bound on the flat rank given the transcendence degree of the field extension, unfortunately. The last notion that I looked at were directions of TDLC group. And first, I will recall some definitions. An automorphism alpha, we say that it moves towards infinity if, in fact, it makes compact open subgroups larger. And it turns out that this is exactly the case when the scale of our automorphism is strictly larger than 1. And so that shows again that the name scale for this function is well chosen. And now we can define the directions of these automorphisms moving towards infinity. And this is done by taking the quotient by some equivalence relation. So we say that alpha and beta, which are automorphisms moving towards infinity. So this is the set of automorphisms moving towards infinity. And we say that they have the same direction if for some natural numbers, k alpha, k beta, and for some compact open subgroup, we have this distance of these compact open subgroups under the powers of alpha and beta is bounded. And so intuitively, this means that, so if we represent the alpha and the beta by points in our space of compact open subgroups, then the powers of the alpha, if it would have a different direction, then this in fact diverges. Then it goes, so it's quite intuitive, in fact, the definition. So this is different directions. But on the other hand, the same direction would mean that this distance stays bounded. One might wonder why these k alpha and k beta are present here. That is to ensure that automorphisms moving like in the same direction but with a different speed are still equivalent. For instance, alpha squared has to have the same direction as alpha. So for that we need those k alpha and k beta will be present, but so we assume that those are natural numbers, otherwise the powers don't make sense. Now, the set of directions of some group of automorphisms is then exactly the quotient of the set of directions moving towards infinity. By this equivalence relation of having the same direction. And so we can also denote the direction, the equivalence classes of these elements by the partial alpha and partial beta. On this set of directions, there is a pseudo-metric delta, and the definition is quite complicated, but I will just draw your attention on the first line. So here we look again at the distance between the powers of alpha applied on the compact subgroup and the powers of beta. But instead of asking that it's bounded, instead of these k alpha and k beta that are in the exponents, now we just look at those powers such that the scale of beta k is inferior to the scale of alpha n. And intuitively, this actually means that they're equally far away onwards infinity. So here beta k is like the best approximation of alpha n. And then we take the limit and make it symmetric. So in general, this is not a real metric, it's only a pseudo metric, and this means that it's possible that so automorphisms have different directions, but lie on pseudo distance 0. And now to continue, it might be useful to just take an extra quotient of our set of directions with the equivalence relation. Alpha is equivalent to beta if and only if they are on pseudo distance 0. So we will look at the direction space quotiented by this this pseudo metric. So now this is a metric space. And then the completion of this metric space, we denote it just by partial A bar, is then called the space of directions. Of A. So recall that we started just with a group of automorphisms of G. Then we looked at the ones who were moving to infinity, so with the scale superior to 1. Then we quotiented, we took the quotients by this equivalence relation to end up with the set of directions. Then we took an additional quotient to make it into a metric space. And then we took the completion to end up with the space of directions. And when we apply this to our example, so we had this alpha, which sends t to the power p, and beta sends s to the power p. And we had this abelian subgroup, which was hence flat of rank 2. And indeed, every element of this this group is a power of alpha multiplied by a power of beta, like this. So we can represent our elements of this flat subgroup by points in the plane with integer coordinates, like this. But in fact, the powers of this element lie on the ray containing this point. And powers of an element are always having the same direction. So we need only one point. So I took here the intersection with the unit circle. And then taking, so we have all these kinds of rays. Then taking the completion of it gives exactly the full circle. There is missing a quarter of the circle because here there are some elements with scale equal to 1, so they can't play along with the directions. So, but the this is the space of directions of this this flat subgroup H, which is 3/4 of a circle, which is quite neat. Now, there is a theorem that says if H is flat, then this set of directions is in fact already metric. So there is no need to take the extra quotients with regarding the pseudo metric. And I was not, but in general this is not true. So there are examples where this pseudo metric is not a metric. But I was not able to produce an example of a Galois group who has this pathology that it's not a metric. The set of directions is not a metric space. So I will leave this as a question. So it would be interesting to know if there does exist a field extension of finite transcendence degree, such that the Galois group has a set of directions. So here, this delta G means that we look at the the group of inner automorphisms and then we look at the directions inside this group, such that it is not metric. And I will finish by explaining why it might be difficult to find such an example, because George Willis gives an example of such a group. And it is defined as follows. So you take a finite group F, and then we take an infinite product. But we don't look at this group, this product with the product topology, but with some other topology which is defined here. And this gives also a TDLC topology on it. But the important thing here is that a permutation of the integers induces an automorphism on this TDLC group. So, for instance, we can look at the concrete permutations subtracting 1, which I denoted by alpha, and also subtracting 1, but skipping the negative powers of 2. And it turns out that these alpha and beta have different directions, but still they are on pseudo distance 0. And why this happens is, in fact, because how this metric and the equivalence relations were defined. So recall that to have the same direction, the definition involved those powers k alpha and k beta, which ensured that alpha squared and every power of alpha would have the same direction as alpha itself. On the other hand, in the metric delta, we looked at to take care of the speed of our automorphisms. We didn't introduce these integers, but we looked at the condition, the scale of beta k has to be less than the scale than alpha n, and this took care of alpha k and beta n to be equally far away on the way to infinity. But in fact, this condition is a bit weaker than the first one, and this allows this kind of behavior, because we see that beta is faster than alpha because it skips some stuff, but it's slower, in fact, than alpha squared. So this behavior is not spotted by the equivalence relation, but it is spotted by the pseudometric, and this results in this fact. But when we would want to try to apply this to Galois groups, it's not that easy, because you can't just randomly skip some elements of your fields. For instance, when we would look at our example that we had for the contraction groups, we had C extended with T and those delta n's, so that the pth power of it was equal to T plus n. Of course, we can do something similar as here. We can shift everything 1 to the left. But yeah, then you can't just skip 1 now, because if you fix that means that T will have to be sent to T minus 1. But to have a field automorphism, T minus 1 has to be sent to T minus 2. You can't just send T delta n minus 1 to delta n minus 3. Yeah, so I don't know the answer to the question, and I will leave it here. But I think it would be nice to know if there exists such a Galois group of a transcendental field extension, or maybe this is a property of Galois groups that this delta G is always that was it. I thank you for your attention, and I would like to hear if there are any questions.
Okay, thank you, William, for your talk. So if there are any questions, either feel free to unmute yourself and ask, or post them in the chat and I will read them out.
I have a question. First of all, thank you for that talk. You've really absorbed a lot of work and a lot of papers there to really put that thesis together and to tell us about them in the talk. But my question is, do you have any feeling about how exotic Galois groups can be? I think the examples you've seen turn out to be groups we're familiar with. You hinted that with your question about directions that there could be some rather exotic examples, but do you really have any feeling for what the Galois groups would be? Can we get anything new?
Yeah, I must admit that I really don't know if such a thing that I said is possible. So I had really to start to look at these transcendental field extensions. So indeed, I got some more of the standard examples and studied them. But I find it difficult to imagine what's possible and what's not. I also saw an article of Zoe Katsidakis, and there she proves something that every TDLC group is the automorphism group of some minimal structure, but I wasn't really able to look into it, what that means and how, if it could be somehow extended to Galois groups. So no, I've not really a plain sight on how wild the Galois groups can really be.
Mm-hmm.
Okay. Any other questions for William?
Yeah, so about the sort of Galois correspondence for admissible extensions, I was wondering if there are any other classes of subgroups that you can sort of identify in terms of the field structure. Like, for instance, is there some significance to open subgroups, like not necessarily compact open?
That's a good question. Not as far as I know of, but yeah, I wouldn't dare to just say no. But I think these compact open subgroups are really one of the more important parts of classes of subgroups of TDLC groups. So that is already good. But I think it's difficult to say just something about open subgroups in general, in fact, because either you don't know if this field here will be algebraic or not. So it's really difficult to then to have a really bijective correspondence, I think. So my intuitive answer would be no, but I'm not sure.
And in another direction, like among the compact subgroups, it's interesting to know which of them have open normalizer. So you've got a theory of compact locally normal subgroups.
Yeah. I didn't really look into that, so yeah, but that would be interesting to know. Yeah, but I'm afraid I will not be able to say something about that.
Okay. Do we have any other questions for William? Well, it doesn't seem like it. So let's thank William one more time.
Thank you.
Thank you. Thank you.
Thank you.
and let's meet after the break.